Okay, so hi everybody, again, starting again. First of all, thank you for coming. I know it's late, and well, on the upside, I can keep you here as long as I want. Oh, no, just kidding. So I work at Riverbed. We do application performance monitoring, and I'm going to talk to you today about how you can optimize the memory traffic of your .NET applications. So first, I'm going to give you some motivation. I'm going to show you some real-life questions and problems that people encounter that have to do with memory traffic. I'm going to show you several ways with which you can identify that you have a memory problem in your application, because obviously you can't start optimizing before you know where the bottleneck is. Then we're going to see a few examples and actual live demos of code patterns, specific coding patterns that can lead to problematic and excessive memory allocations. And finally, we're going to finish with some general recommendations about how you can lower your memory allocation and thus time spent in GC even further. So memory allocation is easy, right? It's cheap. You just have to move your heap pointer. One simple command. It's not free though, and it adds up. And it has side effects on top of adding up, or rather one major side effect, and that's GC. Because the more memory you have, the more GC you need to do, and it takes time. GC has to actually stop your application from running in order to do that memory cleansing that it does. And so the more memory you use, the more GC you need to do, and the GC itself takes more time, and things kind of get out of hand. Big performance problem. And the thing is that, at least from my experience, usually we spend most of the time when we plan our work thinking about optimizing algorithms and mainly our CPU usage. And it's not until we encounter a really severe problem that comes from excessive memory allocation that we suddenly remember, oh, that's right. I should have made that better. I should have optimized that thing. And that's what we're here to talk about. So I'm just going to give you a few examples that I found online. There are really a lot of questions on Stack Overflow that have to do with memory allocation and GC. So here's the first example. Here, there's a guy who's using Unity to write a game. He had some very severe performance problems in his update function. Update is what you do when you need to update your frame, and it has to be really efficient if you want the game to run smoothly. And he actually ran a profiler, and he found that 33% of the time in the update function is GC collect. Now, 33%, that's a third of the time, that's a lot. It's not normal. It's a huge degradation in performance, something you certainly don't want to have inside your update function. Another example, someone is asking why or his code is causing so much GC. He doesn't know why. He wrote a code sample. It doesn't matter in this moment. My point is that he wants to know why it happens. He wants to understand his code. Or another example, someone wants to detect what or who or why someone is calling GC collect. He was using a third-party library, and he had a performance issue, and he had an idea that maybe that third-party library was calling GC collect inside, and he wanted to know how he could check that. So the first thing that we're going to do today is talk about identification of the problem. I do hope that by the end of the talk, you're going to know enough about how .NET works with regards to memory allocation and garbage collection, and you will be able to understand how the code that you write affects memory traffic, and so you will be able to answer these questions and more. So again, let's start with identification, because without identifying the problem, we can't start optimizing. The easiest way, I think, to detect that you have a garbage collection problem is using performance counters. performance counters are available system-wide in Windows. They're built in. They're kind of like these data emitters, which are embedded in different locations in your system. And they can provide performance information, numerical information, about the different areas where it sits. So you can get information about the CPU usage and about memory allocations and disk usage and networking, and of course .NET. And the nice thing about it is that it's available on demand. You don't have to relaunch or recompile, God forbid, your application. You just need to use the right tool to kind of hook inside and see these performance counters in action. So, for example, two available tools for you, which come built in inside Windows, are typeperf, which is a command line tool, which allows you to monitor any performance counter you want in real time, or perfmon, which has a nice graphical UI, which allows you to do the same thing. As a side note, I will mention that you can also create your own performance counters and emit performance information about your own applications, so that maybe the DevOps people or someone else can monitor easily your application in production, but that's not the topic of our talk. So first, let's see how we can use perfmon to realize that we have a problem. I have a virtual machine here with Windows, and I have an application ready for us. It's called Jack Compiler. By the name, you can understand that it compiles something. It's actually an exercise I did for university quite a few years ago. It's a made-up language we used to learn how compilers work. And so we implemented the compiler, and we are going to run this compiler on some big problem, on some big program. Okay, I'm starting, it runs. Now I want to monitor what my application does. So I'm going to run perfmon. Nice graphical UI. I go to the performance monitor area, and it comes ready with displaying the CPU time in our machine. I'm not interested in that right now, so I will just remove that, delete. And I will add the performance counters that I'm interested in, which in this case have to do with memory consumption. So I'm clicking the plus here, and I can see a very long list of groups of performance counters. They're actually grouped into groups by area, by the system that they monitor. So you have energy meter, fax service, file system something, HTTP. Obviously, we won't go over all of them because there's a lot of them. So I'll just skip right ahead to the .NET CLR memory. Where is it? Here it is. To the .NET CLR memory group. I'll expand it, and I can see the actual performance counters. So for example, I'll obviously be interested in the bytes in all heaps. That's the entire managed memory that our application uses. And I can either monitor it for the entire system, or I can select a specific process. In our case, where is it? It doesn't run. I thought I started it. Okay, now it's running. I apologize. Let's try again. Okay, I think I need to close that. Cancel, plus, .NET memory, bytes in all heaps, and okay, here it is. Thank you. I will add it to my list. You can see that we can get information about the number of GC handles, the number of Gen 0 collections, the number of induced GCs, which might be interesting, the number of pinned objects, and so on. I will obviously select the percentage of time in GC. That's a very important metric for me. And I'll also want to see, let's say, the allocated bytes per second. And I will start that, and immediately I can see a real-time graph monitoring these values. Now, in order to see all of them on the same plot, I will have to scale them. Okay? And here they are. Now, the most important one in this case is this blue line, which symbolizes the amount of time, the percentage of time spent in GC. And straight away, we can see it's a problem. It's actually, the scale here for this graph is 1. And so we can see that on average, our program spends about, I don't know, let's say 60% of time in GC. That's totally not normal. So I now know for sure that I have a problem with GC. Do I have a memory leak? Probably not. The red graph here, that's the bytes in all heaps. That's all of my managed memory. It might be high. Well, it's scaled. It doesn't look high, but it's scaled, so it's high. But it's constant. It doesn't change. However, still, we do enough allocations in such a way that the GC is very stressed. OK. So now we know we have a problem. We don't know where it is, though. We don't know what caused this excessive GC. So we know we need to figure out what's going on in our program. Luckily for us, there's another tracing mechanism built in inside Windows, and that's ETW, Event Tracing for Windows. In a sense, it's very similar to performance counters in the sense that it's all over the system. It can provide information from both user mode and kernel mode, from drivers, from services, from .NET, from the file system, networking, whatever you want. It's even inside third-party components like Chrome. It can also be turned on demand just by starting the right tool and analyzing that. You don't have to relaunch or recompile your application. But the big difference compared to performance counters is that this is not limited to numerical data. ETW is actually a logging framework, a structured logging framework, which can provide any data it wants, basically. It supports hundreds of thousands of structured log messages per second, and it has very low overhead, of course, depending on the amount of data that you want to emit. Now, again, as a side note, I'll mention that you can write your own ETW provider, and you can emit your own ETW messages. And again, that's not the topic of our talk, though it's worth mentioning that. So let's see what other data we can get using ETW. This time, I'm going to use a different tool called Purview. It's not built inside Windows, but it is freely available from the Microsoft website. And in fact, it recently became open source. So you can totally use it, enhance it, whatever you want. And this is, although not very visually appealing, a very good functional UI for both collecting and later analyzing these ETW logs. So if I start my application again, and I want to record what's going on in the system, I can go to the Collect menu here. This requires administrative rights, so I will have to restart it as admin. And again, not very visually appealing, but functional. There are a few options here which we can configure. I'm not going to go into much detail because that's not the focus of our talk. But you can see that you can select different areas of the system that you want to monitor, CPU sampling, .NET, .NET allocations, inlining, file I/O, all sorts of stuff like that. Now, I'm not going to collect now, because I don't want to waste time on running the application and collecting the data. But generally, you would just do start collecting, wait a while, I don't know, 10 seconds, whatever, and stop collecting. And after you stop collecting, what you're going to get is a file with the ETL extension. I'm not sure what it stands for. ETLog? I don't know, doesn't matter. And the same application, Purview, is actually able to analyze this file for us and provide very convenient statistical predefined views for viewing these log messages. So the first thing we're going to look at is this view called CPU stacks. Now, I'm not sure if you noticed, but I actually didn't select anywhere in the Collect menu that I want to sample specifically my Jack compiler. And that's because the collection is done system-wide. So I have information here about all the processes that run on my system. So I'm going to select, in this view, my Jack compiler. And the first thing that I'm going to see is this nice table with lots of function names and the percentage of time that the application spent in these functions. And straight away, I can see that 58% of the time, my application spent inside string concatenation. Okay, interesting. Maybe it's okay, maybe not, but that's important information. Now, if I want to know who called that string concatenation, I can double-click it, and it will lead me to this nice, well, I don't know if to call it nice, but this tree call stack view, which will allow me to expand it and see the code path which led me to the call to string concatenation. So I can see that 13% of the time I was led to string concatenation from the assignment function, and another 12% was from the call function, and so on. I can now go back to my code and see what's going on there. Let's look at more views that we have here. We have a memory group. Interesting, right? And we have a GC stats view. Let's open it up. Again, we have information for all of the process on the system, but we're going to select the Jack compiler. And what we can see here is a statistical summary of the GC for my application. So for example, I can see the total amount of allocations, and I can see the total GC CPU time, and I can see the percentage of time the CPU took, and so on. In fact, if I go down, I even get more information about the different generations in the GC. And if I go even further down, I can see a huge list of all of the collections that happened in my application. Obviously, we're not going to look at it now, but the data is there. OK. Let's see what else we can get from this. Excuse me. Here it is. OK. We have another interesting view here, and that's a view summarizing all of the allocations that our application made. And in fact, that's probably what's going to solve the mystery of what's causing our problem. It takes a little while to analyze. OK. Again, we have to select our process, Jack compiler. And OK, how easy was that? 100% of our allocations is system string. Now, combine it with the fact that we know that 60% of the time we were spending in string concatenation, and we know that string concatenations might not be the most efficient thing in the world. That's mystery solved. If I want to know more specifics about where the strings are allocated, like magic, I double-click my type, and I get this nice view, tree-like view again, where I can see where in my program these allocations were made. So, cool. ETW gave us a lot of information. Another way we could solve or look for memory allocation problems in our application is using static analysis. Static analysis basically allows us detecting the problem before we even start running the application. We don't have to wait and run it and like wait for some specific weird scenarios to occur. The idea is that an automatic tool goes over our code and searches for specific coding patterns which are known to be problematic or excessive in allocations. For example, string concatenation, right? I mean, it's really easy to detect string concatenation automatically. You need two strings, and you need a plus operator between them. Sounds like a good Python exercise. Another area where it could help us is try to detect a memory leak even by detecting where we forget to call dispose on our idisposable objects. That's less trivial than finding string concatenation, correct? But still, it's a coding pattern. And once you have a pattern, an automatic tool can do it for you. Of course, static analysis is not limited to just finding memory problems. It can help you in other coding problems as well, like passing the wrong number of dynamic parameters to console write line, or if you try to use an uninitialized local variable, for example. Now, there are several available tools for you to do static analysis, starting from a built-in static analyzer in Visual Studio, ranging through ReSharper, which I guess you are all familiar with. And then you have Coverity, which specializes specifically in static analysis and costs many thousands of dollars per year. So yeah. Now let's try, I don't have Coverity, but let's try to see what Visual Studio could tell us about our Jack compiler, and we can see that we could avoid all of this problem to begin with. So going back to my machine, just close some stuff. Close. Good. I have Visual Studio here. Do you see the code back there? Good. So here is my Jack. Where is my Jack compiler? Here it is. Here's my Jack compiler. We're not going to really read the code now, right? I'll just open a few random files. You'll understand immediately why I do that. And what happens is that whenever a file is open, Visual Studio runs its static analyzer on the open files and emits warnings here at the error list window. Now, I forgot to say that it's not exactly built inside Visual Studio. It's actually it's a free extension available online for free, so it's not a problem. And it's integrated inside Visual Studio. It's called CLR Heap Allocation Analyzer. Its sole purpose is to detect memory allocations in your .NET applications. And so let's look at a few examples of the warnings that this extension emits to us. So let's see. I'll double-click here, and I'll read it to you. It's a little small. Non-value type enumerator may result in a heap allocation. So if you do for each in on non-object, on non-reference type list, you might cause heap allocations. Or another example, here's a good one. Consider using string builder. This is one of our famous or infamous string concatenations. In this case, it's just 2 strings, so maybe it's not that bad. But I actually have more examples here when we concatenate a whole bunch of strings. And so it tells me you're better off using a string builder. Let's see another example, and then we'll move on. Okay, let's do that. No, I like it less. Okay, you can see a lot of string concatenation. We already know that that's the problem, right? Okay, that's nice. What is that? Non-overridden virtual method call on a value type adds a boxing or constrained instruction. So basically, we have a value type here, and we call a virtual method, and it causes allocation. And in fact, we're going to talk in more detail about it in a few minutes. So it seems like we could avoid a lot of problems by just running the static analyzer on our Jack compiler before we started running it. Good. The last method of detecting problems in your application is dynamic analysis. The problem with static analysis is that some problems are still very hard to find and are not characterized by very specific and constrained coding patterns. Moreover, there are some scenarios, such as memory leaks, which are very hard to diagnose without some sort of temporal analysis of what's going on in your programs. And that's what dynamic memory profiling is for. Again, you can do that both on native and managed memory. And there are a bunch of tools available out there. They're mostly commercial. And what's interesting here that you might want to, maybe you're asking yourself, we got a lot of information from ETW, right? And indeed, some of the tools use ETW as the source of their information. However, the main difference between using ETW yourselves and using a commercial tool is that the commercial tool will usually provide a nicer view of the results. It would make some of the analysis for you. It would point you into the correct direction. If you need to diagnose a leak, using ETW, you would have to go over a lot of objects and like count them or whatever. A memory profiler will usually do all that comparison and analysis for you and just give you the results. Okay, that's the type that is leaking. That's what's holding it in memory. Now, running a memory profiler takes a while, so we won't do that now. But I do have a screenshot here from a tool, that's its name, .NET Memory Profiler. Not very imaginative. And what you can see here is that I ran it. It actually also has an extension for Visual Studio. And I ran it on a certain C# application, not the Jack compiler. And I took several snapshots. And then I used .NET Memory Compiler to compare between these snapshots. And it actually tells me that the number of response objects grew from my first snapshot to my last snapshot. This might be a leak. Not necessarily. It's quite possible that it's all going to be freed up in a minute. But it might be a leak. Now, if I want to know what's keeping these objects from being collected, I can just go to another view inside the .NET Memory Profiler. And this time, it will show me that, in fact, there is a static object called response cache. Well, now everything is clear, right? So this response cache, which is static, that's the root that's holding all of my response objects in the memory. At this point, I might decide that this is indeed a bug. I can go back to my code and fix it. OK, so I think we have a good understanding of how we can detect that we have a problem. Now, let's try to see a few examples about how we could reach such a bad state in our application, which coding patterns that we all use, by the way, might lead us to such behavior. So, first of all, I'm going to start with an example. I have lots of Stack Overflow screenshots today. There's a guy here. He's doing some graphics. I think a lot of my examples have to do with graphics. It's interesting. So he has a dictionary of vectors. And what he noticed is that whenever he accesses this dictionary, there is memory allocation happening. And he was surprised because dictionaries are supposed to, well, first of all, he's just accessing. Like, he's not allocating anything himself. He just wants to look inside the dictionary. But also, he was quite surprised because dictionaries are supposed to be really efficient, right? So do any of you have an idea about what might be causing this memory allocation?
Boxing.
Boxing. OK, good. That's the answer I was hoping for. It's the correct answer. Not a trick question. Indeed, it's boxing. But what I want to do next is understand, like, really down to the metal what's going on and what's causing this boxing. And to do that, I will do my own benchmark on something which is a little different, but simplifies what happens in this case. So in just one sentence, I'll remind you that a dictionary is actually a hash table, right? But a hash table has finite size, so some bins in the hash table contain lists of elements, right? The elements that have the same hash function. So eventually, when you access a dictionary, you're going to calculate the hash of your object, and then you're going to have to go through that list of elements and find the one that you're looking for. So what I'm going to do now is that I'm going to benchmark the hell out of searching elements inside lists, okay? So let's imagine that we have a data structure, and it contains a single integer. The guy had a vector, it was 2 integers or 2 doubles, whatever. We're going to have a single member. And then we're going to have a list or array doesn't matter, of such data structures. And we're going to search through them. And the key thing to understand here is that there are actually 3 ways to implement that scenario. The search is always the same, right? We just use contains. We're going to see that in a moment. But the data structure itself, we could write it in 3 different ways. We could either, just let's look at the code instead. It will be much easier to understand. Boxing. Okie dokie. So, don't need that. Okay. So the struct itself, as I said, it's going to hold a single data field. And there are 3 ways to create such a data structure. So we're going to use a struct. We could just, write it the simplest way we could. Struct with a property value. Easy. 3 lines, looks perfect. Then, another thing we could do is that we could override the base equals method that we have in every .NET object. The code is simple. It didn't do anything special. Again, not trick code. We check the type, and we compare the value. Very simple. And then I could even go as far as implementing the I-equatable interface. The I-equatable interface basically says that the type has an equals method which doesn't accept an object, but accepts the type itself. And in this case, when I implement it, it's much simpler because I don't need to check the type. I'll already know that it's the correct type because that's the input of the function, and I just compare values. So those are the 3 different ways in which I could implement such a struct. Now let's look at the test itself. By the way, all the code is available on GitHub. You'll see a link at the end of the slides. I do have some extra test cases here, which we're not going to discuss, but I recommend that you look at them later. It's interesting to try to understand what's going on. So for my benchmark, I'm going to initialize 3 lists of the same size, of course, of these 3 different structures. Now, the initialization, which happens here, is not going to be measured as part of the benchmark because I'm only interested in the search time. And then I'm going to do the search itself. So we have 3 benchmark functions, which are marked with the benchmark attribute. I'll explain that in a moment. And they all do the same thing, basically. Each of them goes over the list, and it asks whether it contains the last element of that list. Why last? Because I want my benchmark to go over the entire list. If it stops after the first one, it's less interesting for me. I kind of want to check the worst case possible. Now, just 1 or 2 sentences about this benchmark attribute here. Correct benchmarking is not easy. You need to think about warming up the cache. You need to think about the overhead of the measurement itself. There's a lot of stuff that you need to think about. And there's a free library online. It's on NuGet. It's called benchmark.net. Again, I'm not going to get into much detail about it, but it just makes your benchmarking life much easier. Basically, you put that attribute on your benchmark functions, and then in your main, you simply call benchmark runner.run and your class with all the benchmarking functions. Whatever you write in the class constructor is not counted as the benchmark. So that's why I have the initialization of the lists in the beginning, in the constructor, and then I have the methods which implement the benchmark themselves later. Now, benchmarking takes a lot of time, so we're not going to run it live. But again, you can totally recreate the results at home. I did prepare the results in advance. Et voila. These are the results. Now, let's ignore the first line for now. I promise I will get back to it later. So let's concentrate first on understanding the difference in the results between the case where we override equals and the case where we implement IEquatable. Notice two things here. The time for the override is longer, and there are memory allocations, while the time for the interface is shorter, and there are no memory allocations at all. Let's understand how that happens. So, how does searching work? Well, it's easy, right? We have our collection. We basically go over it and compare, all of the elements to the element that we're searching for. So, if we're dealing with primitives, for example, it's pretty obvious how to compare them, right? But if we have user-defined structures, it's not so obvious anymore. So we need to create a comparer which is going to compare the elements for me. And it turns out that this is where the difference lies. We can see a snippet from the create comparer function here, and we can see that there's a difference. There is a special comparer created for the case that the type implements IEquatable, and another comparer for the rest of the cases. And if you think about it, it actually makes sense, right? Because after all, if you implemented IEquatable, it must mean that you want to use your own, equality function. So it makes sense. Now let's look at the comparers themselves. So this is the object equality comparer. That's the regular comparer, the one that's used for everything but IEquatable. The code is pretty straightforward, right? That's the key command here, right? X equals Y. Now, what is this equals function? This is just a regular object with no constraints. So this equals function is bound to the base class object equals method, which accepts object as an input. Now, so let's try to understand what we have. We have a struct, which is a value type, and we have a comparer, which calls equals, which accepts an object. We need to pass the value type to an object, so boxing number 1. Y is obviously boxed. What about X? Well, again, X is a value type, right? It's a struct. However, equals is a virtual method. And we need to transform X into a reference with all of its headers and virtual method tables and so on in order to be able to call that virtual equals method on our X. That's boxing number 2. Okay, so now we understand where all that memory allocation is coming from. That's the code for the generic equality compare. The names are really bad, by the way, I have to say. I can't remember which is which, ever. So the code for the equality comparer, which is specific for IEquatable, it looks the same. You can really compare it. It looks exactly the same. Only that, and you can see that in the comment here, that in this case, the equals method is bound not to the object equals object method, but rather to the IEquatable equals method. You can't see that by looking at the code, but that's the way it is. Now, with that information, what's going on? We have the struct. It's IEquatable. We pass it to the equals of that IEquatable. Awesome, no boxing, so -1 box. What about X, though? Now, this is a little tricky, and the reason that X doesn't get boxed either is that the CLR was planned in such a way that calling interface methods on value types is jitted into a direct function call. So this is not a virtual method call. I mean, with structs, you don't have inheritance. It doesn't make sense, the virtual methods. So the JIT transforms this into a direct call. And again, -2 boxes. No memory allocation whatsoever. And that explains the results. Indeed, if we run ETW, if we sample a little bit, our test case with the overridden equals, we can see that, what is that, like 40% of the time in the test was spent on creating new objects. So that really explains what happened to that guy with the dictionary, because his problem was that his vector, the key to his dictionary, did not implement I-equatable. And once he implemented I-equatable on his vector, all of his problems were solved. Cool. Now, I didn't forget that I ignored one, test case, and that's the case where we searched a struct that didn't have any sort of specialized implementation for equals. Now, that has less to do with boxing and memory, and more to do with the fact that the default comparison for structs is not reference comparison, but rather a value member-by-member comparison. And if you don't implement it yourself, .NET is going to implement it for you, but it's going to use reflection and all sorts of very non-efficient stuff, and that's what results in this horrible performance. So if you ever have a struct and you know that you're going to compare it to like anything ever, just, the best thing would be to implement I-equatable, but like at least override the equals method. Okay, so to our next scenario. Another C# goodie, which we all like using, lambdas. Everybody uses lambdas. They're so awesome. They make the code shorter. So a quick explanation about how lambdas are used. How are they compiled? So if we have a lambda which captures a state from its scope, what the compiler is going to do, and that's totally a compiler goodie here, what the compiler is going to do is that it's going to generate a behind-the-scenes class. We don't know its name, we don't see it in the code. And this class is going to have a field, which is the state that needs to be captured by the lambda, and it's going to have a method, which is the actual code for the lambda. And if you want to call that lambda, then you're going to have, well, the compiler does it for you, instantiate this behind-the-scenes class. It will save the state inside the field in that class, and then it will create a new action invoking the method implementing your actual code. Okay. Now, what I want to do is to try to measure the effect of all of this on our code. What I'm going to do is the scenario I thought of that a lot of times we use lambdas in tasks, right? We create tasks, we pass a lambda that runs the code. So what I wanted to do is see how this affects our task creation. So I'll just open it up. Tasks already. Now, since I didn't want to measure the running of the tasks themselves, but just creating the tasks, I wrote a task stub, which doesn't do anything, except that it has the same API as the real task class for creating tasks. So mainly it has two functions. It has start new, which accepts an action, and it has a start new, which accepts an action, and a state which is to be passed to that creation, to that function. Okay? And let's look at the scenarios that we're going to check. So mainly what we're going to do is that we're going to check the case where we have state that we want to pass to the task, and the case where we don't have to pass state to the task. So it's a little artificial example, I know, but let's imagine that we have some data structure and we want to sum up some numbers to a global sum. And for some reason, we want to do it from multiple tasks. All right, so first example, let's say that we want to capture the state, and that's the data that we want to sum up to our global member. So we have a loop, go over the elements, we create our data, and then we start a task with the lambda which captures this data from the scope. Then we could use the fancy task API, and instead of capturing the state, we will use the API which accepts the state as an object, as an input to the task creation function. So in this case, the lambda is actually receiving input. It receives the data as an input, and this input is then provided to the task by the task class, provided to the lambda, by the task itself. And then we have two cases where we don't have any state that we want to pass. So we just have some constant value that we're adding to our tasks. So we just do a loop, starting a new task, adding some constant value, no data to be passed. And another case, well, sometimes we don't have a lambda. We actually have a function with a name. And I could do this sort of silly lambda, right? But ReSharper keeps suggesting that I turn that into a method group, which makes the code much simpler, right? So I just do that. It's nice and easy. So let's look at the results. OK, so let that sink in for a while. These are the results. We're going to see them later again. So let's just analyze case by case what's going on. The first thing, though, that I want to show you is that there's a correspondence in general between the total allocations that we made in our benchmark and the time that the benchmark took. And I think it shouldn't surprise you by now, judging from all the examples that we saw before. So now let's try to understand where all these allocations are coming from in each case. So let's start with the case where we capture state. When we capture state, we have that behind-the-scenes class that we need to instantiate. OK, so we instantiate the class. And of course, we need to instantiate the data itself, obviously. And we save it inside our field. And then we need to instantiate an action which is going to run the method in that behind-the-scenes class that implements our addition to the global variable. So we have three things that we allocate in each iteration. The second case, we pass the state as a parameter. And when the state is passed as a parameter, there's actually no capturing. And if there's no capturing, then we don't have to instantiate the behind-the-scenes class. So in this case, we're only going to need to create the data. Well, we passed the data, so we need to create it, obviously. But then we just use a method which the compiler created for us. It's a method inside a static field. It accepts input, and it implements the addition. And the compiler is actually smart enough to do the action creation just once. It caches it inside a static field. So we have data which is instantiated for each iteration, but again, that's what we wanted. And we have a single instantiation of the action. Those are the cases where we have state to pass. What about the case where we don't have state? Well, that's easy. If we don't have state at all, so we don't allocate the data, we do, however, need an action which sums up this constant value that we're using. And again, the compiler is smart enough to cache it in a static field and instantiate the action just once. Now, here's the most interesting thing, though. You would expect this case to be exactly the same as the last case where I used a named function, right? But it turns out I think it's a bug in the C# compiler. And for some reason, when you use a method group, it fails to do this optimization of creating the action just once. So in fact, you get worse performance than you would have thought. And this pretty much explains the results. So in the first case, you have to allocate data, you have to allocate action, and you have to allocate the behind-the-scenes class each iteration. So that's the worst case. Then the second case, you have to instantiate the data, of course. And, well, basically that's it. You allocate the action just once. So it's better. In the third case, you have the action, which was instantiated once. You don't have data, you don't have state. So that's the best case. And then, sadly, although you would expect it to behave the same, In this case, the action is allocated over and over again, and I guess that the action object takes more space than our data object because it seems that the total amount of memory in the last case is higher than in the case where we have state. Awesome. So now we understand that. And if we join these two things together, boxing plus lambdas, into using our favorite LINQ, right, then we can truly understand that LINQ is the culmination of all evil. Now, sadly, I don't have much time because I don't want to keep you here much longer than you need to. But I will just tell you that I wrote a benchmark doing some mathematical computation, which involved a double loop, one loop inside of another. And I implemented it in 3 different ways. Once, just like using loops. Another time using a single loop and a little helper thing inside from .NET. And once totally using LINQ. You can see the code in GitHub later. Trust me that I implemented it correctly. I checked that the value returned from these functions was the same. And then I ran the benchmark. And I got these crazy results, okay? So the LINQ version is actually almost 10 times worse than the version which just used loops. And look at all of the memory allocation. We see that the memory allocation is about 10 times higher. And as we already saw, there's a correspondence between time and memory. And so, you know what? That's really bad. I can't really say it otherwise. The last demo that I want to show you today is a case of premature allocation. It's a really cute one. Let's see here. Let's imagine we're a web server, and we need to return responses, and these responses are based on lists of collections of results or whatever, which we're going to have to put inside an HTML list. So we could do it in 3 different ways. The most naive representation would be to use a string builder, and that's already, of course, an optimization over just concatenating strings over and over again. But basically, we go over the data, we concatenate the items, and encode the result, and return it. When the data is empty, this loop is not going to get executed, and everything works. A better version we could implement is to cache the empty response, which I saved here. Right? This empty response just holds an empty HTML list. So if I detect that my data is empty, I just return an encoding of the empty list. Or, of course, I could go as far as optimizing this whole thing. After all, why should I encode this empty result over and over again? I'll just cache the encoding, the final encoding result for the empty bytes. And if I detect that there's no data to return, I just return the pre-calculated results. Let's look at the results of the benchmark. Wow, astounding again, right? I think it was rather obvious that the second and the third are going to be better. So the second is like 3 times better than the first one. But the last one, it's basically infinitely better than the first 2. There's nothing on a computer that runs so little time. So it was basically all optimized out. Like, it actually does nothing. And that's obviously the best you could hope for. And imagine this is your web server, which has to answer millions of requests per second, whatever. And this optimization is so easy, you could totally go ahead and do it like right now. Good. So in the time that we have left, I want to give you some general recommendations, like more in a hand-waving style, of more ways you could reduce the stress on your GC and your .NET applications. Again, we're going to have some real-life examples from Stack Overflow. So my first recommendation to you is don't call GC collect yourself, okay? It's okay if you do it for debugging or testing or whatever, but you really need to make sure that you remove it before deploying to production. Because generally what happens here is that you have a memory problem, so you're saying to yourself, well, okay, I'll just go GC collect, and everything will be okay. But you need to trust the CLR, the system. You need to trust the system that it will call GC collect when it says fit. And what you're doing is like putting a patch, like putting a Band-Aid on a bleeding hole in your hand. Because if you have already a memory problem, then calling GC collect will just take up more time, because you have a memory problem, and will cause more pauses and more performance degradation to your application. Instead, you should use all the techniques that we discussed today to, I don't know, like avoid getting the hole in your hand or whatever. No patching. And again, we already saw this screenshot from Stack Overflow at the beginning of the talk. This guy was using a third-party library, and the third-party library people thought it was a good idea to call GC collect, and it just ended up giving more performance problems to this poor guy who was using this library. I'm not sure which one it was. Doesn't really matter. Here's a funny story. In this case, what the guy had, he had a sort of a producer-consumer kind of thing, and his application kept crashing with out-of-memory exception. In a desperate attempt to solve the problem, he put GC collect inside his producer thread. And that solved the problem. Okay, cool. Now, if you go online and read what he wrote next, you would find out that the actual problem, eventually he solved the mystery. The actual problem was that his consumers weren't fast enough. And since they weren't fast enough, they just couldn't keep up with, the producers producing the jobs to do, and memory would just get filled up. So when he put GC collect inside his producer thread, he artificially inserted a delay in producing jobs. So, I put the un in brackets. I don't know if it's fortunate or unfortunate, but this is a really good example of how you patch up the problem and you don't see the root cause. And that's what you need to solve. So that's a cute example. My second recommendation to you is, whenever applicable, which is definitely not always, prefer value types. Value types might be much more efficient to use in case where you have arrays or lists of many data structures because of the way they are stored in memory. Let's first look at the reference types. What happens in reference types is that each object also has an 8 or 16-byte header, depending on your bitness, with all of the metadata and information that it has to store with the object about the type, virtual methods, whatever. So you have the data itself, and then you have the headers, and then, of course, the array itself is made up of references, right, to these objects. And, of course, not to mention that now all of this data is not continuous in memory. Structs, on the other hand, don't incur any extra cost at all. It just packed up continuously in a single chunk in memory. So that's good for caching. It's good because you don't allocate a lot of stuff. You don't do many allocations, and you don't cause many structures that stress out the GC. Now, so I'm not saying you should always use structs, because they do have extra overhead in passing them as function parameters or returning them from functions. But if you have a scenario where you do lots of calculations on arrays of such objects, it's definitely worth considering using a struct. Like, for example, if you do image processing, that's why we have the point to the example here. And this is exactly what happened here in this question. Someone was implementing array tracer in C#. I'm not sure why someone would implement array tracer in C# over C++, but let's put that aside. Vectors are used quite a lot in graphics. He had very severe memory problems and performance problems in general, and they were all fixed once he transformed his vector from being a class to being a struct. So again, based on a real story. Next recommendation is complex reference graphs are stressful on your GC. They cause more cache misses, again, like in the case with the array. So in general, you could replace them with just simple arrays. Of course, it depends on the size, and it's true that a nice object-oriented design would use classes and subclasses and reference and so on, but it definitely has a cost. Another very important recommendation is you should make note of figuring out what your most expensive or your largest objects in your application, and pool them, buffer them, reuse them, however you can, just not to allocate them over and over again. There are many object pool implementations out there. In fact, recently I saw that Microsoft uploaded their own to NuGet. I didn't use it myself, but it has like a gazillion downloads. So I guess if you don't have your own object pool, just try that one. It's going to save you a lot of time. Another idea you could do, especially if you have lots of byte arrays, instead of allocating small byte arrays each time you need one, you kind of manage the memory on your own. You allocate a large buffer to begin with, and you kind of let consumers chunks of that buffer according to what they need. And here you need to take special note that dealing with sub-arrays might cause allocations, like copying or whatever. And so again, there's a library available for you on NuGet. It's called System Slices, and it provides an allocation-free API for dealing with sub-arrays, which is cool. All right, again, based on a real story. And in fact, this one happened to me as well, personally. So I'm feeling very emotionally connected to this one. Again, from the graphics area. Someone was writing a WPF application, and he had to display an image which was updated over time. He was using a bitmap source, and each time he got new data, he created a new bitmap source to display in his application. But the truth is that when you have such a scenario, what you need to use is something called writable bitmap, which provides an API for images that you can update without allocating the pixel buffer again and again. You can simply overwrite the pixels whenever you have new data instead of creating the overhead of a new image. Excuse me. And as we all know, images these days tend to be quite large. The last recommendation I want to give you, the final recommendation I want to give you, is to avoid finalization. It's true that you can rely on finalization to free up your resources, but you don't know when it's going to happen. And in fact, not only do you not know when it's going to happen, there actually might be some weird scenarios that happen with finalization. For example, since finalization happens on a different thread, if you access other objects in your finalizer, you might create concurrency problems. Or there are some other weird scenarios where you can somehow resurrect objects in your finalizer. Or you could accidentally finalize an object which is being used. That's crazy. So, as much as you can, I know it's not always possible, but if you can, implement idisposable and call dispose manually. So that was my final recommendation to you, and that's that. I hope you learned new ways to optimize your applications today. I know I certainly enjoyed timing all that stuff. The results were surprising at times, for sure. Now, just one final note. I know that the differences in the performance seemed huge, but that's because all of my examples were specifically tailored for memory allocation and for the points I was trying to prove. Obviously, not all of your applications are 100% about memory allocation. And not all, but some of the stuff that I showed might make your code less clear, less maintainable, So my final recommendation really is detect the critical code paths in your code. You know how to measure performance. You know how to profile your applications. Detect those critical code paths and optimize them. If you have a 10-node graph, keep it in its reference ignorant bliss, and you will be fine. Thank you so much for coming. I hope you enjoy the rest of the NDC tomorrow, and almost on time.